Hello, welcome back. This is a real pleasure for me because I've been working with Martin Sumner for a few months now. It's been a while. Through the EEF, we started pushing for OpenRiak, which is what Martin's going to talk about. And so this is the first time I've actually seen Martin in person, but we have this monthly meeting where we get together and I say things and he says a lot more intelligent things than I do. So I'm going to let him come up here and say all the intelligent things today. Martin, welcome.
Hi, thank you, everybody. So my name's Martin. I'm an associate at a company called Erlang, based out of Leeds in the north of England. And I'm part of the OpenRiak community, working on the development of the Riak database. And what I want to talk to you about today is how we've evolved Riak over the last few years to make much better use of the BEAM and what improvements that's given us and some of the bumps on the road we've hit on the way. So during this talk, I appreciate that not everyone will know much about what Riak is, but I don't really want to spend 40 minutes talking about Riak because I could easily do that. So I'm going to try and keep it just to 10 minutes and give you a very brief overview about what Riak is and what are the key trade-offs we make in the design of Riak. And then we'll talk then about that evolution of Riak and how we try to make better use of the BEAM and what's gone right and what's gone wrong. And if I leave enough time at the end, hopefully we shall have a couple of minutes to talk about the future of Riak and where we're going in the OpenRiak community. So what is Riak? So Riak is a database, a key value store, or an object store that was based on the Amazon Dynamo paper. And it was first released by the company Basho Technologies, a startup in 2009. If you're familiar with DynamoDB, there's some similarities between DynamoDB and Riak. It's a scale-out database, so typically we have clusters of between 5 and 50 nodes in size. Under the hood, what's going on with Riak, there's kind of two layers to it. Most of the grunt work is done by our backend code or our vnode code, which is a small database, and Riak itself is a collection of these smaller databases. So typically in a Riak cluster, we'll have 512 smaller databases, or another factor of 2 of that magnitude. And above that is an orchestration layer. And that orchestration layer is coordinating activity across those smaller databases. So taking inputs and working out which smaller databases to put those inputs in, working out where to find information, how to resolve queries, but also how to distribute those smaller databases, those vnodes, across the machines and locations that make up the cluster. So when we're developing Riak, our primary aim is to make a database that is very highly available. So I came to Riak originally as a customer. I was building a system that had a 5 nines availability target, always on, no downtime for change. And we built that system on top of a series of Riak clusters. And that system has then gone on to run for a decade with 5 nines availability and with no outages related to database failures over those 10 years. So, that's the core of our customer base, is people that really don't want things to fail ever. But we don't want that high availability to come with particular costs. So it shouldn't require you to run expensive infrastructure, complicated machines, things with high maintenance costs that need to be repaired rapidly if they fail. And neither should it come with a need for frequent operator intervention. So we don't want to be always available because someone's always been woken up in the middle of the night and having to take action to correct something. So we want our operators to be able to sleep. Any interventions required should be deferrable. The cluster should resolve the issues itself. So when we do that, what are the trade-offs that we have to take in order to do that? So, a database can't be everything to all people. And generally speaking, with database, the pain, the negative side of that falls on the application developer, in the sense that Riak won't do some things that you might expect a database to do. So particularly around schema management, around query planning, this kind of thing. It's not going to give you the features that a Postgres might do or that kind of thing. And so where we see Riak deployed is where people have this high availability requirement, but it tends to be either in very sort of strong engineering-led organizations where perhaps they've had a history of databases doing things like schema management and query planning for them and it not going as expected, and they actually want more control over that, or where simply they've managed to resolve their application so it has a very simple functional requirement on the database. Yeah? So that's where we tend to find usage. And when we say high availability, we mean something more than it's just on. And so it's not good enough to be highly available all the time. And if we fail 2,000 queries 1 second and this kind of stuff, all the time what we want is the database to be stable. So by that, what we mean is that it's going to give you a predictable throughput, yeah, through all conditions, and a predictable latency for all your queries, yeah? And that stability should exist under exacting conditions if we're going to be very highly available over a long period. So it should exist when we're maxed out on our nodes, so when all our nodes are running at 100% CPU or 100% disk utilization. We shouldn't depend on out-of-hours windows, because some people won't have a quiet time at 2 o'clock in the morning when something can be deferred to. It should exist for all our functions, not just the simple ones like gets and puts, our queries with filters and deletes and this kind of thing. We should be able to maintain those conditions as we grow, so it shouldn't depend on key counts being keys being small enough to be fit into memory, or objects staying within within small limits. And we should maintain all of those conditions also when failure occurs, but not just when failure occurs, but also when we're recovering from that failure. Yeah, so we don't want to tell operators, well, you can't recover from that failure during peak hours, you've got to wait and work at a weekend to do that. So to give you a flavour of what that looks like, here's some results from our latest testing of our new release, 3.4. And what we do on this test, we run this test twice. We build up a database full with about 150 million objects, a database cluster on a relatively inexpensive set of nodes. It's on some Amazon cloud instances that are costing about $4,000 a month on 8 nodes. And then we hit it as hard as we can with a mixture of stuff: gets, puts, deletes, inserts, updates, queries with filters. And what we want to see is that every 10 seconds, we put a blue dot onto the chart, which represents the throughput at that point in time. Yeah. So what we want to see is the blue dots to stay clustered together. Yeah, that it's stable, that we don't get a situation where it runs fine for 4 hours, then something's got to kick in and it goes up and down. So the blue dot is our control test. Then we go rerun the test, and then we'll invoke some failure condition. So we're at 100% CPU utilization across the nodes in this test, and then we'll go, in this particular one, we'll kick a node, we'll fail it suddenly, we'll keep it down for a couple of hours, we'll recover it, then the rest of the day, the other nodes have to inform it about the data that it's missed. Once it gets back to the full state, it should return to the same level of stability that it had before. And in that failure period, we're running at 100% CPU. We've lost 1/8 of our CPU, so we have to accept that there is up to 12.5% of lost throughput at that point. Yeah, but we want it to remain stable and predictable, and that's the key thing. And so we can do that with a simple failure, and then this is a more complicated failure scenario where we kill a node, we wait for a bit, and then we bring it back with its disk erased. Yeah. So now not only we've got the other node's got to inform it about the updates that have occurred whilst it was down, but about its history of updates, the 60 million objects that existed on that node before then. So it's got to run all of those repair operations, all whilst we're still running at 100% CPU with a node down. And then when it recovers everything and it comes back into play, and then we should return to match the blue dots with the red dots. And then, obviously, when running 100% CPU utilization, we probably don't want to do that all the time, so we want to be able to prove that in that scenario, we can scale the cluster out. So we can add 2 nodes, and during that period, we don't lose throughput we slowly gain throughput, and then when we've added the nodes, we get the additional throughput associated with that. And in this test, the red dots in this case isn't a failure scenario. In the blue dots, the control test, we were testing with a variety of object sizes, but it averaged about 8 kilobytes. In the second test, we upped that from 8 kilobytes to 80 kilobytes. So we go up an order of magnitude of scale in terms of object size. And what you can see is that, yes, the line goes down as we increase the object size, but it only goes down by about 20%. So, an order of magnitude change in object size doesn't lead to that significant a change in the throughput. And one of the interesting characteristics of Riak is that actually the bigger the objects, the more stable the throughput that we can achieve. So I hope that gives you a kind of flavor of Riak, what it is: a scale-out database, a key value store with some simple query functionality. But the aim is to be very highly available, and by that we mean being very, very stable under all kinds of different failure conditions. So what we've done in terms of the recent evolution of Riak, and so by recent I'm really talking about the last 5 or 6 years. So firstly, why do we need to evolve Riak? Why couldn't we just leave it as it is? And there's a couple of key drivers that are going on. As I said at the start, we want it to be a high availability solution, but built on commodity hardware. But what commodity hardware means now is very different to what commodity hardware meant 10 years ago. So, the sort of simple sort of Amazon EC2 instances that we might want to run now are very different to the relatively complicated nodes, and some of the guarantees around availability are different and all that kind of stuff. So that was something which we had to evolve to match. And the other thing is we've got an established set of users, and they had some frustrations about how things worked. The operators wanted to get more feedback on the data that's in the database, how many objects we got, what the object sizes are, how many are in different states and that kind of stuff. We want to improve the queryability so it's easier for application developers. And the key frustration that we want to resolve is that though we talk so far of Riak being a single cluster as a database, most of our users will run multiple clusters with replication between those clusters. And replication is nice and easy to do, and you can do that between various database technologies. It's not very hard, but the difficult thing is reconciliation. Yeah. So if we've got 2 clusters, cluster A and cluster B, both those clusters are meant to have the same objects in. We've got, say, 10 billion objects in each cluster. We want to be able to say efficiently and quickly, are all 10 billion objects the same in both clusters? Even if those clusters are of different sizes and have organized the data in different ways, have different replication factors and that kind of stuff, we want to be able to say quickly, are those 10 billion objects the same? And if they aren't the same, we want to trigger some kind of repair process, because that means that we can have replication without operator intervention. Because otherwise, we have replication. If replication fails or something goes wrong, some operator's got to go check the logs and work out what to replay and that kind of stuff. No, we want to continuously reconcile and in a matter of seconds be able to say, are those 2 groups of 10 billion objects the same? Yeah. So they're the key things that we wanted to evolve and change with Riak. And we knew how to do those, or we had an idea, but we were going to need to redesign. It wasn't going to be simple code changes. There was some significant design work that we needed to do. And as I mentioned before with Riak, there are 2 layers to it. There's this orchestration layer, and then there's the individual database layer, the stuff that's actually doing the heavy lifting. Now, the orchestration layer was in Erlang and felt quite comfortable what we'd have to do to modify and alter that. But the heavy lifting going on the database layer, that needed altering too. Yeah, and there was a lot of change, and we weren't very confident about how we could do that in C++ in a timely manner. Yeah, so what we decided was we would try and standardize on Erlang to make it easier to maintain go forward. So we'd throw out the 20,000 lines of battle-hardened C++ highly performant code and replace it all with Erlang code and do all our heavy lifting with Erlang and see what happens. Now, what we're hoping is that the design improvements we're going to make are going to give us some positive changes, and that will counter expected losses, because all the wise men are looking at that now going, yeah, you're going to go Erlang to C++. You're going in the wrong direction if you're worried about memory and you're worried about CPU. So we went about making that change, and how did things go with regards to memory? So initially with memory, it wasn't such a problem because the users of Riak that had driven the change were largely using on-premise servers that just had a load of spare memory anyway lying around. So we were slightly inefficient with memory, and it didn't really matter. But then they wanted to move to the cloud, and in the cloud everything has a cost, and nothing comes for free. And so they didn't want to have to scale up the size of their nodes just because of the memory. And so memory became an important thing. And we weren't as efficient in terms of memory compared to the old C++ code. And then the other problem that we found is that though the inefficiency was manageable for small key counts, once we got to that 10 billion objects or more level, then we began to see non-linear escalation of memory use that was quite worrying. And when we looked inside the BEAM, we saw big problems with fragmentation of our carriers. So the BEAM was claiming lots of memory and using very little of it actively. So how do we go about resolving that? So the first thing we did was read the efficiency guide, which seems like a very sensible thing to do. And that gave us some improvements, but didn't really resolve the fundamental problem. So we made a bit of a misstep at that stage. Having read the efficiency guide, we thought the next thing to do is we saw all these flags and parameters and this kind of stuff you could do to configure the emulator. And we thought, well, you know what we should do? This BEAM thing isn't managing its memory how we want it to. So let's go and find some magic settings that will resolve that problem for us. So we ran lots of these 48-hour volume tests with lots of different magical settings to try and find the right combination. And in reality, that was the wrong thing to do. We found very few improvements that way and wasted a lot of time. Really what we should have done was read the efficiency guide again. Yeah, and thought about it some more. And the reality is that's what we did do. And the fortunate thing is all that time we'd spent fiddling around with parameters, in order to try and tune those parameters, we'd also spent learning and understanding about how BEAM memory management worked. And with that deeper understanding, when we read the efficiency guide again, we began to understand more about how we should change our Erlang code to make the life of the memory management in the BEAM much easier. And that's what actually gave us significant improvements. So our kind of biggest single fundamental problem was that, like all good citizens of the BEAM, we use lots and lots of processes, because why else would we be on the BEAM? But where typically you would find lots and lots of short-lived processes, we had lots and lots of long-lived processes. Yeah? And so occasionally those long-lived processes would do memory-intensive work, and their heap size would grow significantly. But then it might not do any work for a long period afterwards, so there was no reductions to trigger garbage collection. So we'd end up in a situation whereby we'd just end up with lots of waste laying around on the heaps of all these long-lived processes. So what we realized is we could resolve that quite simply, because our memory-intensive work we could efficiently offload to short-lived processes. Yeah? And particularly if we're going from, let's say, a large binary, which we're going to deserialize, we're going to filter through, we're going to pick a term out of that, well, we can pass that binary to a short-lived process just by copying a reference, so there's no cost to that. We can do all that heavy-duty work in that short-lived process, and then copying the small term that comes out comes at very little cost. So there's very little overhead from offloading that to a new process, and as soon as we finish, that process is dead, and the life of the BEAM's memory management is much easier to handle. Yeah? And we also did various stuff to try and avoid unnecessary copies. So we looked through our binary management code, our list management code, and looked at where we were doing things inefficiently. We converted GenFMs to GenStatums so we could use Hibernate after, and we used Hibernate a lot more within our processes. And we also looked at every loop state that we had in our long-lived processes and actually thought very carefully about what types we were using to store what information and how we could do that more efficiently. The big gotchas that we found around memory are, firstly, the OS kept fooling us about how much memory Riak was using. Because in the BEAM, when it's freeing up some memory from its carriers, it can use a thing called madvise free, not madvise don't need. And perhaps in the very latest Linux kernels, the operating system monitoring can track that correctly, but certainly in the versions we were using, the counters that the operating system monitoring was depending on weren't reduced by madvise free. Yeah? So what was actually happening was that the Beam was releasing lots of memory, but our standard Linux monitoring tools weren't detecting that that process had released the memory, and therefore it was seeing it as still being owned from a monitoring perspective by the Erlang process. So sometimes we were just being fooled. And then the other thing is, and probably, you know, if you search for Erlang memory leak binary anywhere on Google, you'll probably find lots of examples of this. The biggest thing problem is always when we're taking sub-binary references. And our particular problem is that often we would be taking out of larger binaries these small sub-binary references. So in this case, we're taking a type, a bucket, and a key. That's the T, the B, and the K. We're seeing the length of those things and taking them out. And normally, in all our testing, types, buckets, and keys will be less than 64 bytes. Yeah? So we can run a load of tests and everything works fine. There's no memory problems, all of that kind of thing. But if the type, bucket, and key are bigger than 64 bytes, then the handling of that within the Beam memory management is totally different, because now it's going to keep a reference, it's going to make a sub-reference to that part of the binary, and it's got to keep, because a sub-reference is left open, it's got to keep the whole binary memory. So suddenly a user in the real world comes along and implements a new algorithm that defines a new key that's 65 bytes and not 59 bytes like it was the day before, and suddenly using a lot more memory. Yeah, so we had to change our code to make sure where we expected things to be less than 64 bytes, we would also copy anything that was bigger than 64 bytes, so the behavior from a memory management perspective was the same, and then therefore our testing was valid and would get the same results whenever someone would use that with a larger value. So memory we managed to improve off the back of the efficiency guide. When it came to CPU, again, in the early days of making these changes, we were on physical hardware, and so lots of spare CPU was fairly cheap. But then people wanted to move to the cloud, and they don't want to use Intel CPUs, and they want to save money by using ARM CPUs. They want to go from 12 cores down to 4 cores. And so now CPU efficiency becomes a real problem. Now, we knew we had some specific bottlenecks, but we have a lot of Erlang code. And we have a lot of suspicions about where there might be bottlenecks and might be issues. But it's hard to get to the bottom of that when your main kind of verification is a 48-hour full cluster test. Yeah, our loops aren't great. Our cycles aren't great. So the big thing that we did is that we started looking at the Erlang eprof profiling tool and thought, well, this looks quite useful. But we can't really run eprof profiling within a flat-out cluster across the 48-hour test. We need to kind of subdivide our workloads into more testable components. And in those testable components, we need to get a situation whereby we can run 2 tests. One of it, which is something where we can measure and compare reliably between tests, and the other one is where we can run the profile tool. So we had to make changes to code and make changes to tests to make the running of a profiling tool reliable. Once we had that, then that actually gave us some really good guidance to where we were actually spending CPU. And that made a big difference. And so with that, we now had a quicker test fix cycle, and with that quicker test fix cycle, we were able to detect problems, prove they were issues, fix them, and prove those fixes. Yeah. So, and the other thing that's just worth mentioning as a side here, that anything we could do, we realized, to improve the confidence in us making changes was going to help us improve CPU performance. So we spent a lot of time as well expanding around our testings and this kind of stuff to make sure we could be confident in changes that we're making. And so we use a lot of property-based testing of our backends, where we have support in the OpenRiak community community from Quivic, who provide the quick check tool. And recently we've put a lot of effort into using the WhatsApp's equaliser tool to examine the quality of our code. And when we actually found issues through those cycles, well, guess what? We found the efficiency guide triumphed again. Generally speaking, the biggest problem was list handling in areas where we didn't think were going to be important to performance. And it's only when we profiled them that we discovered they were really important to performance. And little subtle changes in how we handled lists could make a big difference. Riak had originally been developed sort of 12, 13, well, actually 15, 16 years ago. So we really needed to modernize some of our data types, and we got automatic performance gains off of that. In very high frequency code, just fiddling around with pattern matching and guards could make a big difference, and some stuff as well around integers helped too. We tried a few experiments with NIFs, because we always assume NIFs are going to make things faster. But actually, once we profiled and had a reliable measuring comparison, none of our NIF experiments really measured up. So in all of that, we only ever added one NIF, which was a NIF to provide a wrapper around ZSTD compression, which we found more efficient than the native compression, which is available within the BEAM. And then the other thing is that with this same test loop, we're able to test OTP versions quite quickly, and we actually found that we're getting a lot of improvements just by doing OTP upgrades. So we realized, look, you know, the right thing to do is keep moving forward, because we get help from the Viking gods for free if we do that. The neat thing as well, as we moved away from using NIFs and C++ code to using more Erlang code, it was the scheduler side effect, in that what we discover is the scheduler does a really, really good job. Yeah? So when we're running these relatively complicated tests with max out 100% CPU utilization, we don't actually do much in Riak to make sure that there's ring-fencing of resources for different types of workload and that kind of stuff. And really, it hasn't proved to be necessary, because the scheduler is really good at making sure that things don't get starved of resource. And we have had situations where, you know, the occasional sleepy developer has released the occasional crazy query running in a continuous loop that's sending everything to 100% CPU. And we had that released into production servers where they didn't notice for a while, in fact, several days, because actually the core gets and puts only changed their performance by less than half a millisecond. So no one outside of the database spotted that someone was thrashing the CPU, scanning 10 million index terms per second. So what's the end outcome of all of that in terms of making these memory and CPU improvements? Well, if we look at our test with the small objects, the red dots and the red trend line is showing what would happen if we ran effectively Riak from about 3 years ago. Yeah? And then the blue dot is showing what we got now, shorn of all the C++ code, replaced with all our Erlang code, and having gone through those efficiency steps. So we've actually made an improvement in the end by moving from NIFs back into Erlang. But small objects is one thing, large objects is another, and when we look at large objects, we see a significant improvement in throughput. In fact, we're pretty much double the throughput we were now in that large objects test. And also, as well as that improvement in throughput, a step change improvement in stability during large objects. So yeah, I mean, I guess a headline might be, you know, we moved from C++ to Erlang and made everything twice as fast. Now, there's a bit of a lie in that. So, you know, if you're in marketing, ignore the next two slides and we'll tell you a bit more of the truth of what's going on. Because obviously the reason why we were moving from C++ to Erlang was that we wanted to change the design, because we had ideas about, from a design perspective, how we could improve things. And this is showing actually the difference, what's going on under the hood. This is graph of disk churn. So one of those is writes and one of those is reads. How many sort of gigabytes per second are we churning on a node during the test? And on the left-hand side is running the old version of Riak, And on the right-hand side is running the new version of Riak. So our design changes transformed what we were doing in terms of disk churn. So although this is a CPU-constrained test, certainly the small object one, one of the big reasons why we got improvements is that by design we'd made things more efficient. And the other thing, and this is going to be quite difficult to see in this, is that as part of the new design of Riak, is that there's certain work that different back-end databases or vnodes who are sat on different nodes can compete to do that same work. So rather than making a decision about which one's going to do it with some algorithm, we actually have a race to compete who's going to try and do it first. And the first one to win the race gets to do the work. Yeah? So that if you're slow in your races, you do less work. And that allows us to provide greater stability because it automatically redistributes load around the cluster. So this is from that test which we showed you before, where we're killing a node and then we're deleting the data on the node and bring it back again. So the node that gets killed is the, well, it looks orange down the bottom on this screen. So that gets killed. And this on the left-hand side is all our query load. Yeah? And when that orange node gets killed, a disproportionate amount of the load falls on the purple and the brown node, so the one at the top and the one four down. That takes up a disproportionate amount of the query load. And so those nodes get particularly busy. Yeah? So what would happen previously is the cluster would slow to the pace of those nodes. Well, what actually happens now, because of the competition for other types of work, when it comes to fetching values, the purple nodes and the brown nodes start losing races because they're busy, so they actually end up with less work. Yeah? And then the other thing they've got to do is repair the yellow, the orange node, the yellowy orange node, and the purple node and the brown node have a lot of data to help with that repair, but they keep losing the races to repair, and other nodes pick up that load, and we end up with a more balanced distribution of CPU across the cluster by having these races take place. Okay, so have we got a few minutes left? We'll just talk a bit about where we're going next with Riak and what we see as being the future of Riak. We've changed a lot to depend on the BEAM in terms of moving most of our code over to Erlang. But one of the things that we're looking at the moment is that improvements that are going on in OTP, how we can make best use of those, and in particular so we can retire code that exists in Riak. So Riak contains lots of optimizations that exist because of things that are now solved in the BEAM, yeah? So there were problems before, and they're no longer problems. So we have lots of code to work around fragmentation of distribution messages, for example, which is now unnecessary after OTP 22, so we can get rid of that. We've got bringing in JSON modules that we've now got a better version, better JSON module within OTP. There's a lot of stuff that we can do better in persistent term, that we're now got all kinds of bespoke code trying to cache things and make things that are like persistent term actually available. And there's some things in the pipeline where we want to improve things using process groups and argparse. We want to simplify the consistency model, and we've got some changes planned to do there. And the big feature that we're working on at the moment is a new query API. And for that, we're using the leaks and YEK tools within the BEAM. And I was a bit intimidated before I started using those, thinking it was going to be really hard. And it's proven to be really easy, incredibly powerful tools. And we're hoping to get some really big improvements on the query side out of making better use of those. So what's going on in terms of our timeline at the moment? Well, back in autumn 2024, we became, actually it's probably worth giving you a bit more detailed history. So when Basho went bust, the assets were open sourced, having been bought off the receiver by one of the Riak customers that was Bet365, and they released that up for the community. But over the last few years, there's been no real structured community around Riak. Yeah, there's just been individual customers working independently on developing the solution. I worked for one of those users. And we were updating the main old Basho GitHub repository, but now what we've done from autumn 2024, we've started a new GitHub repository under the OpenRiak name, and we're actually bringing users and professional services organizations around Riak together under that banner, all with the support of the Erlang Ecosystem Foundation. And we're hoping that's going to help us move forward Riak and give us a stable roadmap that potential future new users can rely on. Over the winter, we've been putting out new versions of our current release of Riak 3.2, and we've been working on the non-functional testing of the next release, 3.4. We're hopefully going to have a release candidate of that towards the back end of spring this year with the new query API in. And then the hard work starts, because in all this time where we've been keeping Riak going from a code perspective and involving the code, we haven't done enough work on the documentation and the clients. And in order to properly release 3.4, there's a lot of stuff we've got to resolve and get together on that. So we're going to be working hard on that over the summer, so that by autumn 2025, hopefully we'll have a new Riak 3.4 that we can point people at and say with some confidence, you can use this and you can rely on the documentation, and it has a future going on as well as a past. So yeah, thank you for that, and you can find us on the Erlef Slack channel. We've got an OpenRiak group, and also we're on GitHub under OpenRiak, and most of our formal discussions take place there on those OpenRiak discussions. Thank you all for listening.
All right, are you ready for the hard part, Martin? We have lots of questions. You're going to have to go through this app when you're done. Luckily, Ted is answering some of them too, but you should probably hop in there. So what industries or applications benefit the most from OpenRiak's architecture?
There's quite a lot of applications within gaming, online betting. So Bet365, who bought the assets off the receiver, are one of the world's biggest. Obviously, DraftKings are here, so I don't think I can say they are the world's biggest. So that's one of the common things. My application that I was working on was critical national infrastructure in the national healthcare space. We've saw quite a few other kind of, I think, Riak gains were past customers. We've seen large online services use it, and there's a very large software as a service provider that is a big user of Riak as well, but they don't like to talk about it publicly, so we can't say who they are.
How is OpenRiak being supported going forward?
Obviously, we have support through if you raise a issue on GitHub and that kind of thing. But there are professional services organizations that will provide support for it, and they're available through OpenRiak, and there's some representatives from one of those organizations, TI Tokyo, here at the conference today, so you can talk to them about professional support. But yeah, hopefully that will grow, and we'll get more people on board.
Nobody? Okay, I have one. Have you benchmarked this against something like S3 storage? Have you tried to look at the difference between using OpenRiak versus S3?
We've done some recent comparisons against DynamoDB, and basically in the use cases that we were testing, there was a significant improvement in latency with using Riak compared to DynamoDB. DynamoDB was quite a bit slower. We're hoping with the new query API especially, there's a lot more flexibility about querying compared to DynamoDB. Obviously, though, it's a very different thing because DynamoDB is a managed service. By default, that's only 3 nines available. And we're hopefully something where if you're prepared to invest in running your own service, it's something that can have that higher level of availability.
Awesome. Well, thank you, Martin.
Cheers.
So it is now lunchtime. And so now that you've fed your head, feed your belly, feed your friendships, and go out there and meet some people. See you.